All right, some details on properties of definite integrals. We're going to just kind of mess with the areas that you can find really well. So just do a little recap here. If I go from the integral from 0 to 12, then I just add together all these. And don't forget the ones underneath are negative. So I'm going to put actually down below 2 pi plus 5, the ones on top, and then the one on the bottom, negative 4. Done. So if you want, you can write this as 2 pi plus 1. Cool. And then if I switch those around, then it's just the negative of those if I ever switch the bounds. So negative 2 pi plus 1. Ta-da. No big deal. So that's a cool property of if you switch the bounds, it just changes the sign of your result. If it was a positive before, then it becomes a negative when you're done. And that's it. That's what you want to remember. And then equivalent pieces. So down below, if I put a constant in front of an integral, remember you can pull that out front as long as it's a constant. And so whatever a to b was, I'm going to give it a number. So if I say the integral from a to b is 7, then k times 7 is just, the k just multiplies that by 7, so it'll be 42. So this is all really groovy like that. So you can just factor it out front, just makes a multiplier. Remember, anything integrated from itself to itself, that's going to be 0. Okay, keep on a rolling. If you reverse the limits, we just saw that a second ago, then you get the opposite area, opposite net accumulation. And then if you integrate from, if I draw a little picture of this, like off to the side here, I don't know what graph this is, but this is A, and here's C, and there's B, because it says in this little picture right here that A is less than C is less than B. C is between A and B. I'm just kind of following the directions here. Then the area from A to C, that's this first integral. And then the area from C to B, just this one there, is the same thing as just doing the whole enchilada together from A to B. You can break it up into chunks. It goes both ways. So you can always split up an integral in the sum of, one area plus another area if you want to break it up into little pieces for any reason. Okay, to the next round. So what that means here is if I get f of x and g of x, and they're both graphical, where'd my g of x go? For some reason, am I missing something here on the old g of x? Is that the one up above? No. Yeah, I'll come back to that one here for a second. I don't know if that's related. Oh, these are not related. Excuse me, pardon that yawn. So this is another one, the addition rule. Like you can always split up the integral of each separately. Like we did with derivatives. Remember, that was always a cool property. You can just split it up. We've mentioned this before. Good time just to recap it. Integrate them separately if you want. And then subtraction, same thing. Integral from a to b, f of x dx minus the integral of a to b, g of x. Okay, and the next chunk, here we go, is, so remember that multiplier rule. So I was just talking about that a little bit ago. If you take a constant times it, so I'm going to do that here in another context. I'm actually going to take it times 3 here, and I'll show you how I break this up. And then 7 to 6, see how those are kind of backward from what you might think they are? I'm going to flip them around. So we use these properties to help us evaluate things that look a little funky. Like 7 to 6, that's a weird order. That's not low to high. So you can turn it around, but when you do, it'll change the sign of our integral. So what I can do is I can get the integral from 6 to 7 of f of x like this. So I got that right here. I'm going to highlight that, and hopefully that shows up on your screen in that yellow. But it's 2, right? You can see that it's 2 blocks. But it's going to end up being negative 2 because I did it in the back order. So integrated from 7 to 6 instead of 6 to 7 like the normal, you end up with a negative. So this would be negative 2. And then same thing happens in number 4. We're going to get this backward thing. 8 to 12 is turned around. So we're going to do 12 to 8. So this is 8 to 12. So if I flip it and make it go the order that I want it to, it's all good. But I can also take another property, which is pull that 3 out. This is an integral. The area, I know the area under f of x, but I don't know what 3f of x is. But it really means just pull that out front, -3 times whatever you get by integrating from 8 to 12 under f of x, which is something I know how to do. It's the area that I shaded over there in orange. Sorry, not in orange. So let's give it at least another shady color. Let's go like this. So this pinky stuff right here, I know how to do that, and that's all this integral here. But when I pull the -3 in there, I'm just going to triple and then make negative the opposite of what I find over there on the side. But let's go check out what I do have over there. What is 8 to 12? Well, 8 to 12 is a triangle that is 1, 2, 3, 4 wide by 2 tall, and it's underneath. I did it up above. It's negative. So we'd call this -4 because it's below, and it's 4 units of total area. But what happens is, I'm going to put that in pink here. That now -4 is what I get with this. Maybe I should just outline this thing. 8 to 12 integral right here from 8 to 12 of the f of x. This pink stuff here, that's what gets me -4. The -3 out in front of it, I just multiply times that number. So this ends up just being -3 times a -4. So I'll put that in top here, which is just that stuff up above. So in all I get +12. Okay, so this ends up being +12. Like that. So this one's 12. Again, I was ready here for emphasis. Kind of wild, huh? So your integrals, the area, we know how to do that. Any multipliers out front, you do after you get the area under the integrals. So integrals, and make sure they go from low to high. If they don't, switch them and put a negative in front. So some pretty cool stuff. I'm going to put a pause on this one, go to the next video so you have a proper length